Welcome to another lecture in the Engineering Design, Modeling, and Graphics series. In this lecture, we will discuss the principles and techniques associated with standard dimensioning. You will learn the process of applying standard inch and metric style dimensions. In addition, you will learn how to dimension different types of geometric features. Be introduced to the many graphic symbols used as shorthand notations in annotating and dimensioning orthographic views. What do we mean when we use the phrase standard dimensioning? We mean the most fundamental techniques and rules of dimensioning, such as the character of the dimension line, the location and spacing of dimensions, the importance of legibility, and so forth. While the American ASME and international ISO standards control many aspects of the dimensioning, there is still much flexibility and choice left to the discretion of the detailer and checker. The ultimate drawing approval is done by the checker and the engineer that signs the drawing. Linear and angular dimensions generally consist of three things: a dimension value, dimension lines with arrows, and extension lines denoting where the dimension begins and ends. Remember, extension lines do not touch the object lines. Diameter and radial dimensions consists of a dimension value and a leader line. Mechanical drawings can use any of these dimensional value styles. The most common in the US is the decimal style. The number of significant decimal digits is based on how accurate or exact a given dimension needs to be. Remember, the more significant digits of accuracy, the more the manufacturing costs will increase. Fractional values are used when calling out the size of the raw stock, or when a dimension need only be accurate to a fraction of an inch. For example, accurate to plus or minus 1/8 of an inch. The third example in this illustration is referred to as dual dimensioning. In this case, the exact inch value is called out with an approximate or reference metric value given in parentheses. This form of dual dimensioning is commonly used if the part is primarily manufactured in the US, but also manufactured in a country whose dimensioning standard is metric. How would dual dimensioning look if it were designed in a metric country but had some parts manufactured in the US? The correct answer is the exact metric value would be placed on top and an approximate inch value below inside parentheses, denoting a reference or approximate inch dimension. The bottom image shows a dimension as a metric value. This looks just like a decimal inch dimension, and for that reason, metric drawings are always labeled or annotated as metric. This illustration and the following one are orthographic views, front, right, top, and two section views of a simple bracket. Here, the bracket is dimensioned using inch dimensions. Notice the number of decimal places used to locate and size each feature. Generally, the author, Giesecke, used 2 decimal places, with the exception being in the section AA view, where he used 2 3 decimal place dimensions. Notice the metric label. All of the 2 place inch dimensions have been replaced with 1 decimal place metric values. In section AA, the 3 decimal place dimensions in the inch drawing have been replaced with 2 decimal place metric values. Why? The answer is quite simple. 1 millimeter is approximately equal to 0.0393 inches. Therefore, in general, metric drawings will always have 1 less decimal place in their dimensions than inch drawings, yet they both have similar accuracy. In the previous lecture, we provided the 2 basic rules of dimensioning. Here, Giesecke illustrates these rules by labeling some dimensions as loc or location dimensions, and others are labeled as size dimensions. The fundamental rules of standard dimensioning are: every feature must be sized, and all features must be located. The next few illustrations are provided to help you understand how to locate different geometric and engineering features. This simple object has 2 bosses rising up from the rectangular base. The cylindrical boss is located off of a center point line. In the view, it is shown true size and shape. The rectangular boss is located off of its corner. In the view, it is shown true size and shape. So any cylindrical type feature is generally located with respect to its center point, and any square, rectangular, or quadrilateral shape feature is located with respect to one of its corners. The point of this illustration is to stress the importance of locating features from controlled surfaces or edges. Here, the cylindrical boss is being located from surfaces that are controlled by finish symbols, meaning these surfaces will be smoother than the other surfaces on this part. Hole locations on some parts seem randomly placed, while other holes are clustered into rectangular patterns or arrays, and still others are grouped as a circular pattern or array. In this example, the 5 holes are placed in a circular, sometimes referred to as a bolt hole pattern. Notice how this pattern is located vertically and horizontally to its center point line. However, this does not completely locate the pattern. It still needs the size of the bolt hole circle, as well as the angle spacing between each hole. If the bolt hole pattern were rectangular, then one of the corner holes' center point would be located to a pair of horizontal and vertical dimensions. Next, a set of horizontal and vertical dimensions would annotate the spacing between the holes. That said, let us return to our circular bolt hole pattern. Is it completely dimensioned? If not, what is missing? We do not know the size of the holes. Notice the holes shown in the top view. They appear to have two circles that define each hole. These type of holes are referred to as compound holes. Compound holes are created from manufacturing operations such as spot face, counterbore, countersink, and so forth. Now look at the annotation underlined in red. This annotation uses some symbols we are familiar with, and others we are not. The X means times or by. The circle with the line through it means diameter. But what does the wide V mean? Its name is countersink, meaning a tapered transition into the hole. So altogether, this annotation says there are 5 holes with a diameter of 0.25 inches that go all the way through the block, and the top of each hole is to receive a countersink of diameter 0.267 at an angle of 82 degrees. Here is a collection of symbols or shorthand notations used in the dimensioning process. I highly recommend that you commit these symbols and their names to memory. Over the next few illustrations, I will explain many of their meanings, which you should also commit to memory. I should point out that your engineering graphics textbook can help with examples and usage of these symbols. The highlighted dimension uses both the by and the diameter symbol to indicate there are 4 holes of diameter 0.375 inches. This highlighted dimension has a box around it. When you see or create a dimension that looks like this, it means the dimension is basic and does not have the general tolerance applied to it. More on this when we get into our lectures of geometric dimensioning and tolerancing. This highlighted dimension uses the diameter symbol followed by a value to indicate the size of the hole. Next, it uses the depth symbol, a downward pointing arrow, to indicate how deep to drill the hole. So in this case, the hole is a 1/2 inch in diameter, drilled to a depth of 0.75 inches. Look in the front view labeled Section AA to see a section or cutting plane view of this simple blind hole that does not go completely through the part. Notice this highlighted dimensions leader is pointed to the outside circle of the compound hole. Reading from left to right on the annotation, we see that the inside hole has a diameter of 1/2 inch and it goes through the part. Next, we see the symbol for counterbore, followed by a diameter symbol and a value of 0.75 inches. Finally, we see this counterbored feature is cut to a depth of 0.25 inches. Look again at the Section AA view to see the cutaway of this counterbore hole. You should be able to read and interpret this highlighted dimension. The internal feature is a hole of diameter 0.25 inches that is drilled to a depth of 0.75 inches. Next, a countersink is cut to a diameter of 0.375 with a countersink angle of 82 degrees. Again, I would encourage you to check the Section AA view to see the cutaway of this compound hole. This slide has 5 highlighted angular dimensions. While most angular dimensions you will create use extension lines, sometimes it is okay to use the object lines of the part to limit the angular dimension. Also, it is generally considered bad practice to place dimensions on the part, as was done with the 161 degree angular dimension. To avoid this, we could have extended the vertical object line with a vertical extension line and defined the edge of the angled surface using an acute angle. This is an example of using reference dimensions to indicate the approximate size of this quadrilateral object. To include either or both of these reference dimensions without putting parentheses around them would have caused this object to be over-dimensioned. Look at the lines labeled smooth edge lines. These are not real edges or transitions that you would ever see on the physical part. The CAD systems put these in by default. However, in orthographic views, they should be turned off and not shown. I have chosen to leave those smooth lines in the pictorial view because I believe they help the novice modeler as they visualize the 3D part. Here we add dimensions to the outer arcs. Instead of duplicating another set of these values, we have added 2 PLS, which means use the specified dimension in 2 places. In this slide, we add the dimension for the 2 circular bosses. Notice the use of TYP, which means typical and can be used to refer to all similar features. In this case, we have only 2, but if the other 2 corners also had bosses of this size, then TYP would refer to all 4 bosses. Dimensioning rounded shapes is always a challenge for the novice. Here are 2 examples given in a way that the manufacturing person would like them dimensioned. In the top example, the compound slot is sized by the center to center length and the specification of large and small radii. The slot is located at the center of the 2 half-inch radii. The manufacturing people like this type of dimension because it tells them what size of cutter to choose, where to place the cutter, and how far to move the cutter to make the rounded slot. The bottom example is also the dimensioning style preferred by manufacturers. Now compare the manufactured style dimensions to what we often find turned in by novice. Both are correctly dimensioned, but the right example appears almost cluttered. They use the 2XR notation to indicate that the radii are full arcs. Your engineering graphics textbook will have shape dimensioning examples, just like these from the Giesecke book. I encourage you to spend considerable time studying these correct, approved techniques for sizing and locating many shapes and features that occur over and over when designing mechanical parts. These are some examples from the Bertolini textbook that show correct techniques for dimensioning compound holes, threads, and grooves. Notice the internal threaded hole. See how the leader is not pointed at the large dash circle, but it touches the object or solid thick circle. We will discuss more about threads and standard fasteners in another lecture. Before concluding this lecture, let's take a few minutes and discuss the takeaways. Number 1, what is the process of applying standard ASME inch and metric style dimensions? What is the process of applying standard ASME inch and metric style dimensions? Metric drawings must be labeled as such. Metric dimension values will generally have one less decimal place than a similar inch drawing. Otherwise, the ASME standard is very similar. What is the process for applying standard ISO metric style dimensions? In general, ISO does not break the dimension line, and the dimension value is written above the dimension line. Horizontal dimensions have horizontally written values. Vertical dimensions have vertically written values. Leaders in the ISO standard are shoulderless, and the annotation is generally written at the same angle as the leader. You should make sure that you know the correct procedures for sizing and locating the commonly found geometric features. Given all of the images of the graphic symbols, could you correctly name each one? And finally, you should become very comfortable in using these symbols to annotate an engineering drawing.